Okay, now uh, welcome to the seminar Geometry, Arithmetic, and Differential Equations of Periods. Today, Andrew Harder is going to talk about Calabi Yau fibered by high-rank lattice polarized K-tree surfaces. Andrew, please go ahead.
Okay. Well, I'd first like to thank Hussein for giving me the chance to speak. It's really sort of a nice thing to be able to speak in Rio. I guess not mind being in Rio, but it's nice to be here. Thank you very much. Okay, so I want to talk today about some work with I guess some collaborators Chuck Duran, Andre Novoselicev, and Alan Thompson. Just to sort of let you guys know, I mean, I do have slides available. I know with these sorts of things, sometimes I maybe go a bit quick. So if you want to like follow along with the slides so you can flip back and forth, I've posted them on my website. So I mean, you don't have to, I guess, memorize this URL. You can probably just Google, me and look at my personal website, and you can probably find this pretty easily. Okay, so I want to talk about a classification of a certain class of K3 fibred Calabi Yau threefolds, and I want to talk about the role that Picard Fuchs equations play in this classification and sort of how they can give us some data about the geometry of Calabi Yau threefolds. So the inspiration for this entire project comes from the theory of elliptic surfaces. So for me, an elliptic surface, or I guess for most people, an elliptic surface is a smooth, for me, I guess, quasi-projective surface S with the proper map from S to a curve C. So I want this to be relatively minimal. So this means that there's no -1 curves that live inside of fibers. And I want the generic fiber to be a smooth elliptic curve. So these things don't need to be themselves minimal. So if you think about maybe a pencil of cubic curves inside of P2, blow up the 9 points in the base locus, this won't be minimal, but it will be relatively minimal with respect to the map to P1 that you get from all of this. So this is an elliptic surface. If you want it to be a Jacobian elliptic surface, you require that there's a section. So this is just a map from the curve to the surface. So the composition is the identity. Okay, so this is elliptic surfaces. So they were, classified, and I'm only going to go over a little bit of this classification by Kodaira. So if I take the smooth locus, I'm going to focus on the part of this classification that's relevant to this talk, I guess. So if you take the smooth locus or the smooth points of this map, then let's just focus on this part. So there are two pieces of data that are important for determining the isomorphism class of your elliptic surface. So the first is the period map. So this is the map that assigns to points inside of the smooth part of the curve the corresponding period in the moduli space of elliptic curves. So that's this guy here. And the second thing is the monodromy representation, which is the local system of H1 cohomology coming from the smooth part of this elliptic surface. Okay, so this data, this is the functional invariant, is what this is sometimes called, and the homological invariant. These two things determine the elliptic surface up to isomorphism. Okay, so I mean, the outcome that I want to sort of, extract from this is that the geometric invariance of the pair S and pi, so this elliptic surface, can be extracted from period data and monodromy data. Okay, so if I want to sort of reduce this data to something else, I can see that both the period map and a large part, not all of the local system information, because the Picard Fuchs equation doesn't sort of know about the integral structure, but at least the complex local system underlying the local system R1 pi 0 of z, this is understood by the Picard Fuchs equation. So so how do you actually extract information from this? I think, I don't know if Cox and Zucker actually did very much, but Stiller is certainly, focused on Picard Fuchs equations and how to extract geometric information from that. Okay, so this is sort of the background. So what we want to do with this is to extend this type of classification to higher dimensions. Okay, so the case that we want to look at, what we want to focus on is K3 fibred threefolds. So for me, a K3 fibred threefold will be a smooth projective threefold or quasi-projective threefold equipped with a proper map to a curve. So C is again a curve. So that's relatively Calabi Yau. So relatively Calabi Yau for me means that if you take a disk inside of the base curve, you take its pre-image, then the canonical bundle restricted to this open subset is trivial. Right? So this is the analog of the relative minimal condition. And I want the smooth fiber of this map to be a K3 surface. So another sort of restriction that I want to place on this is that I want to look at the case where the K3 is, or where the total space is Calabi Yau itself. Okay. So K3 fibred Calabi Yau threefolds, they're somewhat common. They're not everywhere, but they appear in different parts of sort of the math physics literature and the math literature, studying things like Donaldson-Thompson invariants and stuff like that. So they do, they're interesting apart from just this, but sort of for me, this is, I like them because they're sort of analogous to elliptic surfaces. This is sort of my personal take on it. Okay, so the question is, can you provide a classification of K3 fibred threefolds? So in general, this is going to be a hard problem. So one thing that helps make the classification of elliptic surfaces work is that there's a good Torelli theorem for elliptic curves. And in fact, the elliptic curves are parameterized by this quotient of the upper half plane by SL2C. If you want to sort of look at the analogy, the analogous result for K3 surfaces, you see that algebraic K3 surfaces, which are the things that I guess I will focus on today, they come as members of an infinite number of 19-dimensional families. So if I want to think about period maps of these things from especially families of K3 surfaces over curves, these are going to be maps from curves into very large Schmür varieties. So these are, studying this is quite difficult. So if we want to actually understand the classification of K3 fibred threefolds, one part of this is understanding rational curves, or more generally maps from curves to very large Schmür varieties, which seems like a hard task. So today what I want to do is I want to simplify this. So instead of allowing a general K3 surface, I want to force the fibers of this map pi. I want to force this to have many algebraic curves. So what this will turn out to be saying is that we basically force the image of the period map to live in a much smaller Schmür subvariety. And in fact, we're going to force this thing to live in a one-dimensional Schmür subvariety, so that the study of these maps is just maps from a curve to a curve, which is much easier to understand. So what will come out of this is a classification that has a lot of the same features as the classification that I described on the previous page for elliptic surfaces. In fact, it'll be simpler in many cases. Okay, so that's sort of my introduction. This is, where we want to go and the sort of the ideas that go into this. So before going on, I'll say a little bit about Calabi Yau varieties in case there's people in the audience who don't know all this. So for me, a Calabi Yau variety will be a smooth projective variety of dimension D, so that the canonical bundle is trivial and H1 is 0. I'm not necessarily going to worry about being simply connected. I just want H1 to be 0. So a consequence of this, which will be used several times throughout the talk, is that HD0 of x, which is equal to H0D of x, is equal to 1. So this is a necessary condition for something to be Calabi Yau. Okay, so the standard example is a hypersurface of degree d plus 1, or maybe I should be saying d plus 2 in PD. Maybe I should be saying d plus 1 there. Okay, so by adjunction, this is Calabi Yau. So, the type of Calabi Yau whose geometry we're most interested in are K3 surfaces. So these are just two-dimensional Calabi Yau varieties given the definition above. So all K3 surfaces are diffeomorphic to one another. So once they're diffeomorphic to one another, you can compute their Betti numbers. So you can see that the Betti number, the second Betti number of S is 22. all the other Betti numbers are forced to be either 0, so if H1 and H3 are 0, and H0 and H4 are 1. So in fact, these things are simply connected. You can determine the intersection pairing on H2, so this is the topological invariant again. So this is, well, first of all, you determine that it's an even pairing, it's unimodular, just because of Poincare duality, and that its signature is 319. So the signature comes from the Hodge index theorem. So from this, what you can determine is that, in fact, this is isomorphic to the negative definite E8 lattice, so 2 copies of this, plus 3 copies of this U lattice. So this is the unique, even, unimodular lattice of rank 2, which is indefinite. Okay, so its ground matrix is 0, 1, 1, 0. So I'll call this the K3 lattice and refer to it this way. Okay, so another interesting invariant of the K3 surface is what I call its Picard lattice. So since it's simply connected, a K3 surface, the Picard group is isomorphic to the Nernst-Very lattice, which is the intersection of H11 of S and the integral cohomology. So this is a lattice, since it lives inside of H11, the Hodge index theorem tells us that this is a lattice of signature given this way. One rank, its rank minus 1. So an immediate consequence of this, plus the fact that H20 and H02 are equal to 1, is that H11 is equal to 20, so the rank of the Picard lattice is less than or equal to 20. So, okay, so that's the algebraic information associated to a K3 surface. The transcendental data associated to K3 surface is what I'll call its transcendental lattice, and this is the orthogonal complement of the Picard lattice. Okay, so this is the background on Calabi Yau varieties that I think we'll need for this talk. Okay, so I said before that we wanted to restrict our attention to K3 surfaces with lots of curves in them. And so this is done formally by the process of lattice polarization. So I'll take L to be a non-degenerate lattice of signature 1, rank L minus 1, and I'll take S to be a K3 surface. So a lattice polarization is then a primitive embedding of this lattice L into the Picard lattice, right? So the way I chose this lattice was that so that it certainly can embed inside the Picard lattice. If I had a 2 here, there'd be no chance of embedding this into the Picard lattice. And if I had a 0 here instead of a 1, I couldn't have an ample class. So I want this image to have an ample class inside of it, or at the very least, I want some sort of pseudo-ample class. So this data is a lattice polarization. So let's, just to give an example, so the lattice we'll focus on mostly is this lattice Mn. So this is 2 copies of the negative definite E8 lattice plus this U lattice plus negative 2n. Okay, so this is the rank 19 lattice. So if I take a lattice polarized K3 surface with which is lattice polarized by Mn, the geometry of such a thing is very closely related to products to the product of an elliptic curve with an n-isogenous elliptic curve, so a product of 2 elliptic curves. So there's a formal way of saying this due to Morrison, but I won't go into detail about that. So generally speaking, you should think about these things as being geometrically and definitely Hodge theoretically essentially products of elliptic curves, which with an n-isogeny between them. So for an example of a family of Mn polarized K3 surfaces, we can just take the mere quartic family. So this is determined by the vanishing locus of this polynomial here. So generally speaking, a member of this family is going to be very singular. So you can sort of see that even from this equation. If you take the hyperplane W equals 0, the intersection of that with this vanishing locus will be 4 lines. Meeting at 6 points, and so these intersection points will give rise to singular points inside of each of these hypersurfaces. Each of these hypersurfaces, each of these singularities is an A3 singularity. So resolving each of these 6 singularities gives you 18 curves inside of a resolution. Then you take the ample hyperplane class and you get another curve. So that'll span a 19-dimensional sublattice. Then you can just check that this is actually the lattice spanned by these by the lines you get by intersecting W equals 0 in this hyperplane, plus the resolution plus the hyperplane class. This is going to give you an M2 lattice inside of the Picard lattice of each fiber. Okay, Right, so this is the mere quartic family. Actually, I don't know if T, I think maybe I should have 1 over 256 instead of 1 there, but anyway. Okay, so that's the mere quartic family. So what I want to,
is this the same as the dwarf family in dimension 2, or it is different?
I think this is a quotient of the dwarf family. Is that true?
No, I have to check. I have to.
I can never quite remember. I think it's some sort of like high order quotient of the dwarf family.
Okay.
But either that or it is. I'm one of those two is true.
Okay.
Yeah.
Go ahead.
Okay. So now I'll talk about the mere quintic family, and maybe that one's more obvious. I don't know. So a lattice polarization on a K3 fibred threefold is then going to be an L polarization on each fiber in such a way so that the lattice polarization doesn't move with monodromy. So the way you should think about this is that if you take the bundle of, say in this case, H2s associated to the fibers of this map, right? So this is R2 pi of, say, Z. Then there's a trivial sub-local system whose stalks are isomorphic to L. Right? So there's a fixed L polarization. So the basic example of this, which I won't talk about the details of too much, is the mere quintic family. So it's presented this way. So this is quite analogous to the way I presented the mere quartic family. And so the fact that this admits, so really this is a singular, a very singular family of quintic hypersurfaces. There is a smooth resolution of this family which admits a fibration by mere quartics, but it's not necessarily true that every smooth resolution does. Okay, so that's the mere quintic. Right, so it's fibred by mere quartics, so it has an M2 polarized K3 fibration structure on it. So as I said, there's definitely expressions for this family where the mere quartic fibration is obvious, where you can sort of see that this is obtained by taking some sort of variable change from this expression here, maybe exchanging the t with some fermion t, but it's not completely obvious from the way I wrote it here. But that does exist. Okay, so you can compute this. Okay, so this is sort of the things that I want to study. So once I induce a lattice polarization, what I said before is that imposing the lattice polarization on the fibers of your K3 fibration means that your period map is restricted. So I want to explain now in which way the period map is restricted. So let's assume that I have a lattice polarization. I actually called this something else in the previous slide. Anyway, so this is my primitive embedding. This is iota here. So this is a map to the K3 lattice. So take just this raw data to begin with, and let's, we want to classify all of the K3 surfaces for which this L lives inside of the Picard lattice. Okay, so I'm going to give you like a very brief overview of the moduli space of lattice polarized K3 surfaces. So I'll define this fellow, which I'll call PL. So this is all points Z inside of the projective space given by taking the orthogonal complement of the image of this iota and tensing with C. So this is going to be a projective space of dimension, let's see, so if L has rank something, then this is 22 minus the rank of that, then subtract 1. Then I take a quadric inside of this, so things whose pairing with themselves, and so the pairing here is given by the pairing on the K3 lattice. So the pairing is equal to 0, and then I want to look at only essentially half of these points, or not really half. I want to take out some real hypersurface inside of here, and I want to just look at where Z pairs with its complex conjugate is equal to 0. So generally speaking, this will be something with two components. And if I restrict to the case of Mn, right, so this very big lattice, this rank 19 lattice that I'm mostly interested in, what I get is not, well, okay, I'm sort of lying here. It's not just the upper half plane H, it's two disjoint copies of the upper half plane. But I'm just going to maintain this fiction for the moment. Right, so you can sort of see that this is probably what you should get just from this expression. Right, so if my lattice here is rank 19, the projective space of its orthogonal complement is 2-dimensional, right? So yeah, the projective space on a 3-dimensional vector space. Then I cut it down by taking a quadric, so that'll bring us down to 1 dimension. A quadric is going to be 1-dimensional quadric, so that's P1, and then I just take out a real hyperplane here, so that'll sort of, you can think about that as splitting by taking out the meridian S1, and that'll give you 2 copies of essentially H. Okay, so that's what happens here. So this is essentially the period space of possible pod structures with the fixed isomorphism to the K3 lattice. So if I want to remove a marking from this data, what I do is I take a quotient by this group gamma of L. So this group gamma of L is going to be essentially, you should sort of think about it as some finite index subgroup of OL per. So this should say iota of L. So it's a finite index subgroup of this, and these are just the things that come from elements of the orthogonal group of the K3 lattice, which fix the lattice L, or the image of the lattice L. Okay, so this is some big wild thing, but in the case where L is equal to Mn, you can check that this is actually isomorphic to gamma naught of n. So this is the classical modular group, and plus means that I add the Frickett involution to this. So it's some order 2 extension of this classical modular group. Then if I want the actual moduli space or period space of L polarized K3 surfaces, I just take the quotient of these 2 things, and you can sort of see that this is going to act properly on that. Great, and so what we get out of this is a modular curve if L is equal to Mn. Okay, so the point of this whole exercise is to say that if I want to think about the periods or moduli of Mn polarized K3 surfaces, well, the period maps are going to look like maps from a curve to a modular curve. And this is very similar to the case of elliptic surfaces, where the period map was a map from a curve to, instead of gamma naught of n plus, it was just SL2Z. So it's a very similar situation in terms of just period maps. And so just coming back to our analogy, so we now want to try to talk about the classification of Mn polarized K3 fibred threefolds the way we talked about the classification of elliptic surfaces. And if you sort of think through all this, you know, apply the Torelli theorem and blah, 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 what you get is this theorem. So if you have a K3 fibred threefold, so nothing about Calabi Yau here, just the K3 fibred threefold, so that there's an Mn polarized lattice polarization on this, and if n is not equal to 1, then we actually can do better than Kodaira's theorem. We can classify these K3 fibred threefolds by just their period maps so from the base curve to some compactification of this modular curve, or maybe smooth compactification, normalization. Okay, so this is very nice. So why is n not equal to 1? So in some sense, so there's this issue if you think about elliptic surfaces. The period map is essentially enough to classify these things if you don't have local monodromy which multiplies by -1. So this is why you have to introduce the homological invariants to account for the -1s that can occur in local monodromies. So with Mn polarized K3 fibred threefolds, if n is not equal to 1, then you can't have this phenomenon of -1 monodromy around a singular fiber. But if n is equal to 1, you can have such a thing. So that's why things are a bit more complicated in the n equals 1 case. So this was worked out by Koistra and Thompson more recently. And they actually came up with sort of this beautiful classification of M1 polarized K3 fibred threefolds, which is very closely related to the classification of elliptic surfaces. Right, and so, I mean, in that case, actually, the K3 surfaces that they're dealing with are Hodge theoretically essentially the same as products of self-products of elliptic curves, so it's not really too surprising that you get an analogy with elliptic surfaces. It's essentially what you would expect. Okay, so great. So now that we've gotten this theorem, we have we know that these K3 fiber threefolds with Mn lattice polarizations, they're classified by their period maps. So the question is, given a period map, can the total space, can the K3 fiber threefold that has this period map, can it be Calabi Yau or not? So I want to detect this, and this is where Picard Fuchs equations are going to enter the equation. Right. So this is the plan. So before getting into that, we have to make some sort of reductions. We have to figure out. We have to reduce the problem a bit, and the main tool that at least I use for this is the degeneration of the Laurent spectral sequence. Okay, so if you have a proper map to a curve, then this goes back to Zucker essentially. So the Laurent spectral sequence for this proper map degenerates at the E2 term to give you this decomposition. So Hn splits as a direct sum non-canonically, but it splits these cohomology groups. Okay, so I plus j equals n. So the first consequence of this is that if we assume that our total space is Calabi Yau, well, remember that I said for me a Calabi Yau has h1 equal to 0. So, so just writing out what this degeneration of the Laurent spectral sequence says for h1, we see that h0 of r1, this is equal to h0 of r1 plus h1 of r0. So forgetting about this term, I mean, this means that both of these two things are 0. So in particular, h1 of r0 is equal to 0. So since our fibers are connected, the sheaf r0 pi of q is just the constant sheaf. Therefore, h1 of the constant sheaf on the curve is equal to 0, which means that the curve is p1. Okay, so there's a very direct way to deduce that the base of any K3 fibered Calabi Yau threefold is equal to p1. This is irrespective of anything else. This is just, if I have a K3 fibration on a Calabi Yau threefold, the base is p1. Okay, so now I want to, so this actually says something about, a little bit about this classification. So I mean, the period maps, the base of this period map C has to come from a p1. Furthermore, if this period map is non-constant, then this also says that if I have an Mn polarized K3 fiber threefold, which is Calabi Yau, then this modular curve, H mod gamma naught of n plus, this has to be itself rational. Okay, so there's a finite collection of those things. They're classified. So we get some information about that as well. So an immediate consequence of this is that there's a finite number of n's, so that there's an K3 fiber Calabi Yau threefold with Mn polarization. Okay, so that's sort of one nice consequence. But this doesn't tell us very much. This is a very broad classification. You can have gamma naught, H mod gamma naught of n pluses, which are rational, for which there are no corresponding K3 fibered Calabi Yau threefolds. So we have to do a bit better than that. And the way to do this is to study the transcendental variation of hot structure on the internal K3 fibration. Okay, so just to set up some data, let's let sigma be the set of singular values of pi, so our K3 fibration, and let's let I be the embedding map from sigma to P1, and J be the open embedding from the complement of sigma to P1. Okay, so what does the Laurent spectral sequence say in this case? So by essentially messing around with sheaf theory and stuff like this, you can reduce H3 to a direct sum of simpler sheaves. So more generally, so if I just write this out, I have three factors. Then I want to reduce what I have to look at in terms of the cohomology of these three factors to two different things. So you get immediate vanishing of H2 of R0. Oh, sorry, R1, because R1 is well, it's a fibration by K3 surfaces. So the R1 sheaf is going to be a skyscraper sheaf. So I want to take H2 of that. I'm going to get 0. Then by playing around with standard stuff in sheaf theory, you see that you have splitting in terms of these two things. Okay, so the first piece So this is a pullback onto the singular fibers of the R3 sheaf. And then you extend by 0. So this tells me that what I'm getting from this is information about the cohomology of the singular fibers. And then the other component of this is what I get by pulling back the R2 sheaf to the smooth locus and then pushing forward. So when I pull back the R2 sheaf to the smooth locus, I get a local system, and then I push it forward. So this is something that's telling me about the local system, and this is essentially data about the cohomology of smooth fibers.
Andrew, it seems to me this has to do with Lifshitz decomposition. Is it true?
Lifshitz decomposition.
I mean, for this decomposition, you need a polarization for X, or it is independent?
I'm not entirely certain.
Okay. Okay, maybe later I will have a look at it again.
Yeah, no, this is probably true. It's probably just that I don't know this. I mean, maybe the Lifshitz decomposition. I don't use any sort of. I mean, for this is just a pure sheaf theory computation here. Okay. Maybe somehow that's involved in the decomposition of the Lattice spectral sequence, and I'm just not aware of it. I'm not entirely certain.
I mean, do you need that X itself is polarized? I mean,
yes, yes.
Okay.
Yeah, but that comes in the degeneration piece. Yeah.
Okay. Okay.
Yeah. Yeah. Okay. So great. So now I have this decomposition into two pieces. I want to focus on the second piece, and in fact, I want to reduce what I have to focus on in the second piece a little bit. So since what we're looking at is actually an L-polarized K3 surface, this means that this local system has a big trivial piece. So this is the trivial piece. So if I want to take H1 of that, I get H1 of the first thing, the trivial piece, is going to be 0 because I have my base is P1. So really all that I have to look at is the cohomology of this transcendental piece. So this is stuff that lives inside of the algebraic cohomology, inside of the Picard group of every fiber. And the second piece is stuff that doesn't live inside of the Picard group. Okay. Okay, so according to Zucker, these two pieces independently carry pure Hodge structures of weight 3. So I mean, this is just saying that the pure Hodge structure of weight 3 on H3 of X can be transferred to pure Hodge structures on each component. This is a decomposition in terms of Hodge structures. Okay, actually, so it should be a lower shriek, not an upper shriek. Okay, so now what I want to do is determine these Hodge structures. So I mean, just some very broad qualitative stuff about this. So if I look at H0 of this push forward sheaf, this extension by 0 sheaf, the cohomology in this is type 0A0. So this is H0. This just means H30 is equal to 0 and H03 is equal to 0. And this is just because this comes from H3 of some surfaces that live inside of singular fibers. And H1 is of type BCCB. So this means that H30 can be non-zero. So really, if I want to detect whether my total space is Calabi Yau, all I need to focus on is the cohomology of the transcendental local system. And in fact, I want to focus on the pure Hodge structure on this cohomology group. Okay, great. So that's really the upshot. The upshot is that if I want to determine, so first of all, I have this restriction on the base curve, and the second thing is that I have this this deduction that I just need to look at the transcendental local system and its push forward to the singular part in order to determine whether my total space can be Calabi Yau or not, because this won't say anything about it. The singular fibers don't actually contribute to the transcendental part, if I can say that, of the Hodge structure of a Calabi Yau threefold. They will contribute to the canonical bundle. So if you actually want to say geometrically whether this is Calabi Yau, you have to be careful about what lives in singular fibers or not. But if you just want to say, can this thing be Calabi Yau? Does it give you a Calabi Yau Hodge structure on H3? That's just determined by H1 of the push-forward sheaf of the transcendental local system. Okay, so now the question is, how do we check whether what we have is Calabi Yau? Okay, so now we want to study variations of Hodge structure a little bit more in detail. Actually, maybe I should ask, when should I stop speaking?
I mean, it is supposed to be 55 or 1 hour, so you have something like more 20 minutes.
Okay, sounds good. Thank you. Okay, so great. So I want to just briefly talk about what a variation of Hodge structure is and some data associated to it. So I have a smooth curve with a Q local system on it, or integral local system, depending on the coefficients that you want to take. I have a flat bundle, so this is just what I get by tensoring with the structure sheaf of the base. So this is the variation of Hodge structure curve. And then I have the connection on this flat bundle, which I'll call nabla. And then on this, I want to equip a filtration. So this is a decreasing filtration by subbundles, so that when I restrict to a given fiber, what I get is a pure Hodge structure on the stock of weight d. Okay, maybe d plus 1 given my, no, d, okay, d, sorry. Okay, and so the last thing that I require is that Griffith's transversality holds, so that if I apply this connection to my Hodge bundles, I can move up in the Hodge filtration, but not by that much. Okay, so this is the basic data. And so a little bit more fine is what is called the quasi-canonical extension of this variation of Hodge structure. So we can't extend the local system V to a local system on U, but we can extend the Hodge bundles to bundles on all compactification of U. So this will be F bar. So we can also extend the connection nabla to a logarithmic connection. So this is, I'm not explaining how this is done, but this can be done in some sort of nice way. So we extend to a logarithmic connection, and so I'm going to let these EID minus I's be the quotients of these extended bundles. Okay, so what I want to say now is that essentially we can use these quotient bundles of the extensions of the Hodge bundles to determine H30 of so there's a pure Hodge structure on this H1 of the push forward of T, and I can determine H30 of this using the cohomology of the Hodge bundles. Okay, so this is the theorem of Delange, Mueller-Stack, von Straten, and Swope. So this part is sort of more what they prove, and this is an extension of work of Zucker, the first part. The second part, I'm listing this as a theorem of theirs, but this is more like a classical statement. They give a proof of this, but I think it's more like a classical statement. So this tells me that if I want to compute just the rank of H1 of this thing, then what I need to do is I need to take the rank of the local system itself, so the transcendental local system. So gamma of P is the local monodromy around a point P. So this is essentially the rank of the co-invariant lattice at each singular point. And then there's some contribution from the curve itself. So in fact, there should be a -2 rank T. So, I'm stating this theorem as if it were an extension of the previous slide. But really, this is done in general. So I'm sort of simplifying their result here. Okay, so the moral of this story, or the moral of all this, is that if I actually want to determine H03 or H30 of the canonical Hodge structure on this H1 of the transcendental local system, what I need to do is I need to compute just the degree of E02, because really what I'm doing is I'm computing H1 of a bundle on P1. So this is just, there's nothing to really compute except the degree. Okay, so we've reduced the problem to computing the degree of some bundle on some curve. Okay, so great. So now how do I actually compute this degree? I want to explain the process here. So I have to introduce this invariant, which is called the parabolic degree of the Hodge bundle. So I'm not going to explain what exactly this is, but this is essentially some invariant associated to these quasi-canonical extensions, which computes data about the degree of the bundle, and then it's going to also compute some sort of data about how I extend it over singular points. So this is actually going to be a possibly rational number. It doesn't need to be an integer. And the rational part just comes in to sort of measure how quasi-unipotent the monodromy around each singular point is. So if I have just unipotent monodromy, this parabolic degree is just degree. But if I have quasi-unipotent monodromies, local monodromies, then this is going to have some fractional components. Okay, so one nice characteristic of this is it says that it sort of flips in some way when you change P and Q. And for us, the main consequence is that this means that if I take the parabolic degree of E11, I get 0. Okay, so that's the big takeaway. Okay, so what this means is that, so if this is some invariant that gives me information about the degree and local monodromy, it means that if I can compute the local monodromy part of this parabolic degree, I get the degree of E11 for free. Okay, so I just need to have some data about local monodromy, and I can get the degree of E11 as a bundle on P1. Okay, so that's kind of nice.
Is this extension that you took is this Deline's extension? Because there are many extensions to singular fibers.
Yeah, it's Deline's extension, yeah. So I want, I'm trying to remember exactly. Yeah, so I think does it make sense to say that this is the one where the, so you have a V filtration on each, on the extension to each singular fiber, and I want this V filtration to have filtrans between 0 and 1.
Okay.
Yeah, so this is doing this extension, yeah. Okay, so yeah, I'm not entirely certain what would happen if you change the extension. You might be able to run the same game, but you have to pick something in some sort of regular way for this to work. Yeah. Okay, so great. So from this information, I can compute the degree of E11, but that's not quite what I wanted. I wanted the degree of E02. So in order to get the degree of E02, I try to study maps between E11 and E02, and so this comes from what I call, or what is called, the Kadairos-Spencer map. So just by taking the Gauss-Menin connection nabla, I can get an induced map between these Hodge bundles E1, Eij and Ei minus 1j plus 1, right? Okay, so good. So now I know the degree of E11. I can compute that, and I have a map from E11, in this case E02. So if I can compute the degree of this map, I'm good. I can compute the degree of E11. So this is now the goal. The goal is to compute the degree of the Kadairos-Spencer map. So this is something that Eskin, Kintsevich, Muller, and Sorich tell us how to do. They tell you that if your Hodge bundles all have rank 1, then you can compute this degree, or the co-kernel of this map, using the Picard Fuchs equation. That's really sort of the moral here. It's that you can compute this map using the Picard Fuchs equation. So this is where Picard Fuchs comes into the whole story. So in particular, the condition that these ranks are all equal to 1 is satisfied if we have a lattice polarized K3 surface with MN polarization. So now this reduces our strategy to the following. So we want to use local monodromy data to compute the degree of E11, and we want to use the Picard Fuchs equation to deduce the degree of E02. Once we have that, we can determine whether our original family of K3 sources could have been Calabi Yau or not. Okay, right, so we have this data. So what is the Picard Fuchs equation? So I'll maybe briefly go through this because I want to maybe emphasize the main points of this. So the Picard Fuchs equation is going to be some sort of ODE that annihilates the periods of the family of K3 surfaces. More precisely, what you do is you take your relative canonical bundle over the curve, and you choose a section of this, and you can induce a pairing between this relative canonical bundle and this transcendental local system, or more generally the local system of cohomology, which is essentially integration. So I'm writing this in terms of cohomology. So I need to, when I integrate, I need to introduce Poincare duality into this. I could also take the wedge product of some Durham representative of tau. Okay, so you get this pairing. This is relatively standard. Then you can start taking derivatives of these periods, these things here, and see what comes out. So how does this work? Well, so the bundle, this F0 bundle, which is this tensor product of the transcendental local system and the structure sheaf, this is a trivial bundle over U because it's just the bundle over an open subset of P1. So this means that if I take some fixed section sigma of the Hodge bundle, and I start to hit it with the Gauss-Menin connection, and at each point I pair again with the vector field d by dt, what I get is just a bunch of sections of F0. This is a trivial bundle over O0. So if I do this enough, I'll get a linear relation between what I get by hitting this with the Gauss-Menin connection. So I can express this linear relation over OU as a relation like this. Then I try to translate this into an equation, a differential equation, saying something about derivatives of periods. So my periods are these integrals. So if I take tau to be a local section of this local system for some open subset, then what you can sort of deduce is that pairing the Gauss-Menin connection with this tau. So this is taking the period associated to the Gauss-Menin connection associated applied to sigma is the same thing as taking the derivative of the period. So translating that into a statement about these this equation here, we get that the local sections are the periods of this family of K3 surfaces are annihilated by this differential equation. So this is the Picard Fuchs equation, Picard Fuchs ODE. It's a nice differential equation and has regular singularities. So at the bottom here is just a remark that this depends on my choice of sigma, but for our purposes, choosing a different sigma won't change the result. Okay, let's see. Great. Okay, so now let's try to state this theorem of Eskin, Kincevich, Muller, and Sarch. So we need this local data about Fuchsian ODEs. So the singular points of a Fuchsian ODE, if you express it with a sort of a monic differential equation, the singular points are just places where these HIs are meromorphic or properly meromorphic at 0. So you can sort of localize this around each point, and you can check whether your ODE is singular. So it's going to be regular if these are sort of holomorphic in a nice way, and Fuchsian if all singular points in P1 are regular. You can deduce from this the indicial equation. So if you assume that 0 is singular, you can rewrite this differential equation in terms of this new differential operator. Then you write down this indicial equation, which is a polynomial essentially coming from our operator in terms of this new differential operator. And the characteristic exponents of this differential equation at a given point are just the roots of that equation, arranged by size. Okay, so very quick. Maybe people know this already. Great. So what do Eskin, Kincevich, Muller, and Sarch say? So they say that if you have a variation of Hodge structure on P1 with some singularities, of course, so that the Hodge bundles all have rank 1. Then you can deduce the length of the co-kernel of sigma I of these Kodaira-Spencer maps at each point in terms of the characteristic exponents. So if you have an apparent singularity of your differential equation, so this is a place that is a singularity but whose monodromy is trivial, then the length is given just by differences of the characteristic exponents. And you have to do something a little bit different if you have an actual singularity, so somewhere where the monodromy is non-trivial. So places where the apparent singularities will have integral characteristic exponents, actual singularities might not. So in fact, you just have to take the floor function of these things and take their difference. Okay, so this is what they say. So they give you this formula in terms of the differential equation, which tell you how to compute the length of the co-kernel of this map. Okay, so we can go through the example of the mirror quartic family. And so let's do all this computation. You have this nice, well, okay, for the sake of time, maybe I won't do this computation. If you're interested, you should take a look, because this actually tells you exactly what to do. So in general, if you have an L-polarized family of K3 surfaces, you can use this plus the strategy that I outlined before to give a precise formula for the essentially H03 of this family of K3 surfaces in terms of data coming from local monodromy. Okay, so the first thing that you need to notice is that there is a classification of the local monodromies of any Mn polarized K3 surface fibred family. So this is essentially some sort of group theory type thing, and you can just deduce that it looks like local monodromy must be some power of one of these matrices. Okay, so let's write this out. And then we just sort of define these somewhat arbitrary invariants, A1/2 and AF. This is just a way of organizing into groups different singular fibers which give different contributions to parabolic degrees, essentially. Okay, so they're counting, I mean, these things can count the same points in both categories. Just this is some bookkeeping device. And so the main theorem that we have is that if we have an Mn polarized family of K3 surfaces over P1, then E02 is equal to OP1 of whatever this thing is. So, right, so let's just break down this equation. This is an equation, so this somehow corresponds to the fact that this is somehow some canonical bundle piece. This counts points with certain contributions to parabolic bundles, this one as well. And this computes something corresponding to the co-kernel of the Kodaira-Spencer map. Okay, so this is our equation. It's not a very transparent equation or a very nice equation, but it is an equation where all the pieces can be computed from the Picard Fuchs equation. Right. So this is just very this is a very functional thing. And so the point is just that given an example of a K3 fibred Calabi Yau threefold, if I know the Picard Fuchs equation of the internal fibration, I can tell you whether this can be Calabi Yau or not just by looking at this equation here. Okay. So let's see. So a problem that we can sort of look at is to try to figure out whether this can be done for lattices which aren't Mn. So this just comes down to classifying the local Picard local monodromy invariants. Okay, so I will go through this very quickly. So if you apply this formula to the case of the quintic threefold, you can get this very nice result that you deduce that the Hodge numbers are 1, 1, 1, 1. And so this is classically what is known to be the Hodge numbers on H3 of the quintic threefold. So classically, it's known that these are the Hodge numbers. So you can recover this just from the internal Picard Fuchs equation. And maybe this is too fast, so yeah, so maybe I'll just finish with this. So we get this nice equation coming from Picard Fuchs equations for whether, I mean, this essentially computes a Hodge number of a K3 fibration. And then the remaining Hodge numbers, or things that we expect are some contribution to the remaining Hodge numbers, come from the rank of this local system itself, which is, again, a local monodromy computation. Okay, so I'll stop here since I'm at the end of my time, but maybe I'll leave, if you're interested, the rest of the slides are online.
Okay, thank you very much, Andrew. Okay. We will have 2 sessions for questions. The official one. Let me see. Okay, maybe Andrew, something. I think you were one aspect of all this computation is that you want to prove that H30, the Hodge number H30, is equal to 0. But always.
Or 1 or whatever, yeah.
But well, when the canonical bundle is trivial, this implies that this number is no H30 equal to 1. When the canonical bundle is trivial, then it implies this that this Hodge number is equal to 1. But the vice versa, I am not sure. I mean.
Yeah, it's true. It's true. The converse can be false, definitely.
But the actual, let's say, the canonical bundle is trivial. Which computation is involved? All this computation of the Riemann scheme, or?
Right. So if you want to actually talk about the canonical bundle as such a thing, this has more to do with the singular fibers than the smooth fibers. So this is something about can I force the it's a hard birational geometry problem essentially, and it depends on the actual singular fibers you're dealing with, and can you get a nice model of these singular fibers. So in the cases that we're most interested in, these M2 polarized K3 fibrations, we actually haven't worked out like. We have a good sense of what the possible singular fibers look like, and for in many cases, and we can show that in most of these cases, you can actually do this. You can actually force the canonical bundle to be trivial around these singular fibers by choosing the right birational model of these things. But you can certainly like destroy Calabi Yau by just blowing up in singular fibers and doing stuff like this, and it's just hard to control.
Wait, some extra work rather than this computing Riemann schemes, initial equations, and so on.
Sorry,
work to really prove that the canonical bundle is trivial.
Yeah, exactly. Yeah, so this is sort of an approximation. So the use of all of this is that it reduces the amount of work that you have to do in birational geometry to check something is Calabi Yau or not. You only have to check a certain number of cases. Without this, so just to talk about the history of this whole project. So we worked out the M2 case without anything involving differential equations. So this was essentially Alan Thompson doing, as I said, hard birational geometry. You take a family of K3 surfaces, you take a cover of these things ramified along very singular fibers, and you try to figure out when this cover is going to have a smooth Calabi Yau model. And so he did this, but it was hard. Like he really had to look at very fine information about resolutions and things like this. So with this Picard Fuchs equation approach to the problem, we were able to give necessary conditions for this thing to be Calabi Yau. And at that point, all you have to do is check that these are sufficient conditions. That if you have this space change, you check that you can actually get a Calabi Yau model. But without this, I mean, there's a lot more checking to do in birational geometry, which is hard. Or to me, it's hard, much harder than this.
Okay, so maybe let's, I stop recording and we go to the informal session.